Welcome to Deep Thinkers. Tonight, I want you to hold a single, strange object in your mind. Picture a lens. Not a lens of glass, not a lens of plastic ground in some factory, but a lens of stone, a clear, transparent piece of rock, smooth and curved, no bigger than a grain of sand. And now I want you to understand something that almost sounds like a story told to soothe a child, except that it is true, completely and verifiably true. Roughly 500 million years ago, there was an animal that looked at the world through eyes made of exactly that. Eyes made of stone. And if you went to the right museum drawer in the right quiet back room and lifted one of those fossils into the light, you could press your own eye close and look straight through a lens that once watched an ancient sea. You would be looking through the same window some long-dead creature used to see. The same crystal. The same curve. 500 million years between you, and yet somehow you are sharing an instrument of sight. The animal was a trilobite. You may have seen one before, fossilized, that flat, segmented shape, a little like a horseshoe crab, the kind of thing that turns up in gift shops and on the shelves of people who love old stones. And most of the trilobite, when it died, became what fossils usually become, a faithful copy in some other mineral, a ghost of the original pressed into the rock. But the eyes were different. The eyes were already made of mineral while the animal was alive. The lenses of a trilobite's eye were built from calcite, which is calcium carbonate, the very same substance that makes up limestone and chalk and the shells of clams. A transparent crystal of it, grown by the animal itself, shaped into a working lens. So when a trilobite died and the soft parts rotted away and the rest turned slowly to stone, the eyes did not need to be replaced by anything. They were already stone, they simply stayed. Which means that among the countless eyes that have ever existed on this planet, the trilobites are nearly the only ancient ones preserved in their original optical material. Every other eye you can imagine, the eye of a fish, a bird, a dinosaur, a person, was made of soft, wet tissue, and soft, wet tissue does not last. It rots in days. It leaves almost nothing behind. But the trilobite kept its eyes in stone, and so we can do the impossible thing. We can look through a 500 million-year-old lens and see, in some small way, what it saw. I want you to sit with that for a moment, here in the quiet, with your own eyes growing heavy. There is an animal long gone that has been dead for longer than you can really feel in your body, longer than the dinosaurs, longer than the continents have held their current shapes, and yet a working piece of its eye still exists, still bends light the way it always did, waiting in a drawer in the dark. That is the kind of thing that should be impossible. And it is the thread we are going to follow tonight, slowly, gently, all the way down into the strange and beautiful question that hides behind it. Because here is the question, here is the thing that historians of life, the people who read the deep past out of the rock, still circle and argue over and cannot entirely close. It is not only how an eye could be made of stone, it is something larger and stranger than that. It is this. There was a moment, somewhere in the long story of the earth, when life first opened its eyes. A moment before which nothing could truly see, and after which the seeing never stopped. And nobody knows not exactly what the world looked like in the instant before that switch was thrown. Nobody knows with certainty who saw first, the hunter or the hunted. Nobody can fully agree on whether the eye was simply one more thing that life happened to grow, or whether the eye itself was the spark, the trigger, the cause of one of the most dramatic transformations in the entire history of living things. That is the mystery we are going to walk into tonight. Not to solve it, because some of it cannot be solved, but to wander through it slowly, the way you wander through a quiet old house, room by room, in no hurry at all. And before we go further down, before the lamp dims and we descend into that ancient ocean together, I would love to know where you are tonight, where in the world you are listening from, what city, what country, what quiet room. Leave it down in the comments if you feel like it, because I do read them. And there is something I find genuinely comforting about knowing that all of us, scattered across the whole lit surface of the planet, are lying in our separate rooms in the dark, drifting toward the same old story. And if you are new here, if you have only just found this quiet corner, you might want to subscribe so the next slow journey finds you when you need it. That is all. No rush. You can do that now, or you can simply let it go and stay where you are, because tonight we are going somewhere very far away and very far down in time, and I want you to come slowly. We are going to travel back to a moment roughly 538 million years ago, give or take, to the threshold of a span of time that geologists call the Cambrian period. And we are going to stand at that threshold and look both ways. Behind us, the world before eyes. Ahead of us, the world after. And the difference between those two worlds, the before and the after, is one of the deepest divides in the whole history of life. So let us go back, all the way back, to the world as it was the instant before anything could see. To get there, we have to step back even further than the Cambrian, into the period that came before it, a long stretch of time called the Ediacaran. The Ediacaran ran from roughly 635 million years ago to about 538 million years ago, and it is named after a range of hills in Australia where its strange impressions were first found, pressed into ancient stone. I want you to imagine that world now, because it is nothing like the ocean you know. There are no fish, there are no crabs scuttling along the bottom, there are no sharks, no jellyfish quite as you would picture them, no coral reefs full of darting color. There is no chasing, there is no fleeing, there is in fact almost nothing in that whole sea that you would recognize as a struggle. Instead, picture a sea floor, dim and still, lit only softly from above where the sun filters down through the water. And growing up from that seafloor, anchored in place, are the living things of the Ediacaran, what scientists call the Ediacaran Biota. They are soft, they are quiet. Many of them look like fronds, like leaves or feathers, standing upright in the current, swaying very slowly as the water moves. Others look like flat discs lying on the sand, or like quilted mattresses, like segmented pads pressed gently against the floor of the sea. They have no shells, they have no spines, they have no claws, no teeth, and, as far as anyone can tell from the marks they left behind, no eyes. They mostly do not move, or move so little that movement is hardly the word for it. They are rooted, sessile, content to stand where they are and let the world come to them. And the way they feed, the way they take in what they need to live, is perhaps the gentlest detail of all. Many of them appear to have fed osmotically, which is a way of saying they simply absorbed nutrients directly from the water around them, the way a paper towel soaks up a spill, the way the roots of a plant draw moisture from the soil. They did not hunt, they did not graze, they did not need to. They stood in that soft current and let the dissolved richness of the sea pass through them, taking what they needed without ever lifting a limb against another living thing, because they had no limbs to lift and there was nothing to lift them against. A scientist named Mark McMenamin gave this vanished world a name that I find almost unbearably lovely, and I think you will too, here in the dark. He called it the Garden of Ediacara. A garden, think about what that word carries. A garden is peaceful. A garden does not chase you. A garden has no predators stalking through its beds, no creature lying in wait, no flight, no fear. The plants in a garden simply grow where they are planted, soaking up the sun, swaying in the wind, unbothered. And that, more or less, is what the Ediacaran Sea seems to have been. A garden of soft, still, patient things, standing rooted in the dim light, asking nothing of one another, taking what they needed from the water itself. There was no arms race in that garden, because there was no race at all. There was nothing to outrun, because nothing ran. There was nothing to hide from, because nothing was hunting. The whole logic of pursuit and escape, the logic that fills every ocean and forest and field today, simply did not exist yet. It had not been invented. I want you to really live inside that for a while, because it is so different from everything that came after, and so different from the world your own body was built for. Imagine being a soft frond on that Ediacaran seafloor. You stand in the gentle current. The light comes down from above, blue and faint, growing dimmer as it sinks. Around you, your neighbors stand the same way, swaying, soaking, silent. Nothing approaches you with intent. Nothing watches you. Nothing means you harm, because nothing in your world is capable of meaning anything at all toward you. You are not prey because there are no predators. You are not hidden because there is no need to hide. You are simply there, alive, absorbing, untroubled, in a world that does not yet know how to be cruel. There is a kind of innocence to it that almost aches. A long, slow, dreaming peace that lasted not for years, not for centuries, but for tens upon tens of millions of years, an unimaginable stretch of quiet, far longer than anything we would call history, far longer than our minds can really hold. And it was a peace that was going to end, not slowly, not gently, but that is getting ahead of ourselves, and we are in no hurry tonight. Stay in the garden a little longer with me. Feel how still it is, because the stillness is the whole point. The stillness is what makes everything that came next so astonishing. When you understand how calm the Ediacaran world was, how soft and slow and unhurried, then you understand the size of the change that was coming. It is the difference between a sleeping house and that same house when every light comes on at once. The contrast is the story. The before is what gives the after its meaning. Now the Ediacaran did not last forever. Time moved as it always does in its slow geological way, and the world began, almost imperceptibly, to change. And we arrive at one of the great boundaries in the history of the planet, a line drawn in the rock that scientists place at roughly 538.8 million years ago. That line is the beginning of the Cambrian period, and the Cambrian is where everything we are talking about tonight truly happens. It is the doorway between the old quiet world and the new restless one. On one side of that doorway, the garden. On the other side, something that has been called, for more than a century, an explosion. I want to be careful with that word, explosion, because it is the word everyone reaches for, and like a lot of words everyone reaches for, it can hide more than it reveals. When geologists speak of the Cambrian explosion, they do not mean a single instant, a flash, a bang. They mean a period of remarkable rapid change when an enormous variety of new kinds of animals appeared in the fossil record in what is, by the standards of deep time, a very short stretch. The most intense part of this transformation is concentrated roughly between 538 and 515 million years ago. The major groups of animals, the great body plans that almost every living animal still belongs to today, appeared across a window of around 20 million years. 20 million years. Say it slowly and let it stretch out. To you and me, 20 million years is an unfathomable amount of time. It is far longer than there have been humans of any kind on the earth. It is longer than the great apes have existed. If you tried to count it out second by second, you would never finish. And yet, set against the 4.5 billion years of the Earth's whole life, set against the tens upon tens of millions of years, the Garden of Ediacara stood quiet and unchanging. That window of 20 million years is fast. It is geologically fast. It is the difference between a glacier that takes 10,000 years to crawl down a valley and one that suddenly, in a single season, lurches forward. So when scientists call it an explosion, they mean it the way you might call a slow-blooming flower's opening sudden if you watched it over weeks and then sped the film up. Compressed against the vast, slow patience of the deep past, 20 million years of transformation does look like a burst, a flowering, a switch thrown, but it is still longer than a single blink. It is still longer than a single breath of the world. Hold both of those truths at once, here in the quiet, fast and yet unimaginably long. That doubleness is part of the strangeness of deep time and part of why it is so soothing to sink into. Everything that feels urgent to us happens in the spaces between heartbeats of the planet. And in that window, in that 20 million year flowering, the world filled up with animals. Where the Ediacaran garden had been soft and still and rooted, the Cambrian seas began to fill with things that moved, things that had hard parts, things with limbs and shells and segments, things that crawled and swam and burrowed and, crucially, for the first time, things that could see. The body plans laid down in that window, the basic architectural templates of nearly every animal alive today, have persisted ever since. 500 million years later, they are still in use. The arrangement of your own body, the very fact that you have a front and a back, a left and a right, a head where your senses cluster, a long line of nerve running down behind, all of that traces back to decisions made in that Cambrian window, templates set in those ancient seas and never abandoned. When you lie down tonight and feel the shape of your own body against the bed, the bilateral symmetry of you, 2 arms, 2 legs, 2 eyes facing forward, you are wearing a design that was drafted in the Cambrian and has never gone out of fashion. It is, in a very real sense, the oldest piece of architecture you own. But the question we keep circling, the deep one, the one that historians of life still cannot fully close, is why? Why then? Why did the long, slow, peaceful garden suddenly, after all those quiet eons, begin to flower into all this restless complexity? What changed? What threw the switch? For a long time, people simply marveled at it as a mystery, the Cambrian explosion, sudden and unexplained, a riddle in the rock. And there are many ideas about what drove it, and we will sit with several of them in time because honesty matters in a story like this, and no single answer has won the day. But there is one idea in particular, one beautiful and contrarian idea, that turns the whole story inside out. It suggests that the eye was not just one of the many new things the Cambrian produced. It suggests that the eye, the first true seeing eye, may have been the thing that started it all. That vision was not a feature of the explosion. Vision was its fuse, and to feel the full weight of that idea, you have to first really understand what a world without seeing is, which is exactly the world we have been standing in together, the Garden of Ediacara, the soft, quiet sea before the switch. Because in that world, light fell, but nothing read it. The sun came down through the water, the same sun that warms your window in the morning, and it touched those soft fronds and discs, and they did nothing with it, the way a stone in a field does nothing with the light that lands on it. Light was just there, ambient, unused, an ocean full of information, photons streaming down by the uncountable trillion, carrying within them the shapes and positions and movements of everything in that sea, and not a single creature able to gather it, to focus it, to turn it into knowledge. The light fell on the blind, and the blind did not know it was falling. Think about what that really means, here in your dark room, with your own eyes closed. In that ancient garden, an animal might be inches away from another, and neither would have any way of knowing the other was there until they touched. There was no seeing across a distance. There was no glance. There was no recognizing a shape on the horizon of the seafloor and reacting to it. The whole sense we rely on most, the sense that fills your waking life so completely that you forget you are using it, simply was not available. Imagine living your entire existence able to feel only what touched you directly, to taste only what reached your skin, to know the world only at the very edge of your own body, and nothing beyond. That is the sensory world of the garden. Small, close, immediate. A world without distance, because distance is something only sight can really give you. Without eyes, the far is the same as the empty. If you cannot see it and you cannot touch it, then for all practical purposes, it is not there at all. And so the garden could afford its peace. With no creature able to perceive another at a distance, there could be no stalking, no ambush, no pursuit, no flight in advance of danger. You cannot run from what you cannot detect, and nothing could detect anything beyond arm's reach, if it even had arms. You cannot hide from a hunter who cannot find you. And there were no hunters, because hunting at a distance requires, more than anything, the ability to see your prey. The entire machinery of predator and prey, that vast and ancient dance that drives so much of life's drama, depends on one creature being able to locate another before contact. And that ability is at its root the ability to see. Take away vision, and the whole bloody beautiful theatre of the chase simply has no stage to play on. The garden was peaceful not because its creatures were gentle by nature, but because they were blind by nature, and a blind world is, in a strange way, a safe one. There is nothing to fear in the dark when nothing in the dark can find you. And here is where the mystery deepens, and where I want to leave you tonight, on the very edge of the change, so that the next stretch of our journey can carry you the rest of the way down. We know the garden was calm. We know the Cambrian that followed was a riot of armor and motion and hard parts and, yes, eyes. We can read both worlds out of the rock, the before and the after. What we cannot read so easily, what the stone does not simply tell us, is the order of events in between. Did the eye come first and force everything else, the armor, the speed, the burrowing, the fear, into being? Or did the world grow busy and crowded for other reasons, the chemistry of the ocean shifting, the oxygen rising, the genetic toolkit of life unlocking new possibilities, and the eye merely arrive among that crowd as one more clever invention? Who saw first, the hunter or the hunted? And what, exactly, did the world look like in the final quiet instant before any creature anywhere opened a true eye and, for the very first time in the long history of life on this planet, looked out and saw? That instant is the hinge of everything. On one side of it, a garden that had stood in peaceful blindness for tens of millions of years. On the other side, an ocean that would never be calm again. And somewhere on that hinge stands a zoologist named Andrew Parker, and an idea he called the light switch, an idea that the sun itself, falling unused for so long on a blind and peaceful world, was about to be switched on as a weapon. But that is where we will go next, slowly, gently, when you are ready. For now, just stay here at the threshold with me. Stand in the last of the garden's quiet. Feel the soft current, the dim filtered light, the patient swaying fronds, the deep unbroken peace of a world that does not yet know how to be afraid. It is the calmest place in the whole history of life. And it is about to end. But not yet. Not yet. Stay a while longer in the garden, in the dark, in the quiet, and let the old peaceful sea hold you the way it held everything before the first eye opened. And before we follow Parker down into his idea, before the switch flips and the long piece breaks, let me tell you where in the world I imagine you are right now. Wherever that is, some city by the water or a quiet room far inland, if you feel like it, leave a word below and tell me where you are listening from tonight. I read them, and there is something in knowing that a story this old is being heard in so many places at once. And if you are new here, if you have just wandered into the dark with us, you can stay, subscribe, and these slow journeys will keep finding you one buried mystery at a time. There is no hurry to any of this. Tonight, we are going to walk all the way back, slowly to the moment life first opened its eyes, and you may fall asleep long before we arrive, and that is perfectly all right. The story will still be here. The garden will still be here. So let us stay in it a while. Picture the sea floor as it was in the Ediacaran period, the long stretch of time that ran from roughly 635 million years ago down to about 538.8 million years ago, the last great age before the world changed. Lower yourself into that water in your mind. It is shallow and warm in places, dim and green, lit by a sun that no living thing has any use for yet. And across the soft mud, anchored and swaying, are the strangest gardens you will ever fail to recognize. Fronds, discs, quilted, ribbed, leaf-shaped things, some no bigger than a coin, some longer than your arm, standing or lying or fastened to the floor, rocking faintly in the current like a meadow underwater. These are the Ediacaran Biota, the first large, complex living things to leave their shapes in stone, and almost nothing about them looks like an animal you know. They have no mouths that anyone can find, no guts, no limbs, no faces, and, most importantly of all, for this story, no eyes. A paleontologist named Mark McMenamin gave this vanished world a name that has stayed with it. He called it the Garden of Ediacara. And the name fits, because that is what it was, a garden. Not a hunting ground, not a battlefield, a garden. Think for a moment about what that absence means, lying there in the dark. In a garden like this, there was, as far as the rocks can tell us, almost no predation. Nothing chased, nothing fled. Many of these soft creatures seem to have fed without ever moving at all, simply absorbing nutrients straight through their surfaces from the water around them, drinking the sea in by osmosis, the way a root drinks from wet soil. They did not need to find food, they did not need to catch it. They needed only to hold their place on the floor and let the gentle chemistry of the ocean pass through them. There was no reason to be fast, because nothing was fast. There was no reason to be armored, because nothing bit. There was no reason to hide, because nothing was looking. Let that settle over you. Nothing was looking. For tens of millions of years, life on this planet got larger, got stranger, got more intricate, and through all of it, no creature anywhere could see another. They lived pressed up against each other in total mutual blindness, sharing a world none of them could perceive. A meadow of living things that never once met another's gaze, because there were no eyes in all the world to meet. It is, when you sit with it, almost unbearably peaceful. There is no anxiety in a world like that, no watchfulness, no flinch. The fronds sway, the discs rest, the light falls unread upon the mud, and the slow rhythms of the sea continue, day into night into day, and not one living thing knows the difference between them, because not one living thing can tell light from dark in any way that matters. The sun rises and sets over the garden of Ediacara, and the garden simply does not care. It cannot. It has no instrument to care with, and then at the far edge of that long quiet, the boundary comes. Around 538.8 million years ago, by our current best reckoning, the Ediacaran ends, and a new chapter of the Earth story begins, the one we call the Cambrian period. The line between them is not just a line on a chart of rock. It is one of the most important thresholds in the entire history of life, because just on the other side of it, the garden begins to fill with astonishing speed with creatures that look, for the first time, like animals. Things with mouths and guts and limbs, things that move with purpose, things with hard parts and sharp parts, things that before very long will be able to look at one another. We tend to call what happens here an explosion, and in the slow arithmetic of geology it deserves the word. But it is worth being precise about it, because the precision is part of the wonder. The most intense burst of this transformation, the time when most of the great branches of the animal family tree, the major body plans that still organize nearly every animal alive today, appear in the fossil record, is concentrated into a window running from roughly 538 million years ago down to about 515 million years ago, 20 million years, give or take. That is the span of the explosion at its hottest. Now, 20 million years is not a moment. It is not a single dawn, not a switch thrown in an afternoon. It is a stretch of time so vast that the human mind cannot hold it, an unbroken depth of seasons and tides beyond all counting. And yet, set against the whole long age of the Earth, against the billions of years of life that came before, and the 500 million that have come since, 20 million years is a thin, bright seam in the rock. It is the geological equivalent of a held breath. In that one narrow band of time, the blind, soft, peaceful garden becomes a sea of moving, hunting, fleeing, armored, watching things. The templates get written, the body you carry, the plan of it, the deep architecture of it, is drawn up in those 20 million years and has barely changed since. The molecular clocks, the slow ticking of mutations counted in the genes of living animals, hint that some of the lineages had quietly begun to diverge from one another, even earlier than this, before they left any trace we can read in stone, so the roots of the change may run a little deeper than the fossils alone reveal. The rock and the genes do not always tell exactly the same time, and that is its own small mystery for another night. But on the surface of the record, in the layers we can touch and date, the change is sudden and it is enormous, and it is concentrated right here, just past the boundary, in the early Cambrian. So hold both of these in your mind as you drift. On one side, the garden, blind and calm and unhurried, stretching back for tens of millions of years. On the other side, beginning right here, the long bright seam in which everything you are descended from learned in geological terms almost all at once, to move, to hunt, to flee, and at last to see. And it was a zoologist who looked at that seam in the rock and asked the one question most people had not thought to ask. Not what appeared, but why then? Not what the fossils looked like, but what could have caused so many different lineages in so many different places to begin building armor and eyes and weapons at what was, geologically speaking, very nearly the same moment? His name is Andrew Parker. He works with eyes, the optics of them, the physics of light moving through biological tissue, the engineering hidden inside structures that were grown rather than designed. And sometime in the 1990s, sitting with the fossil record in one hand and the optics in the other, he arrived at an idea that was, in its simplicity, quietly stunning. He called it the light switch. The book he eventually wrote about it was published in 2003, and its title borrows from the thing you do without thinking dozens of times a day. In the blink of an eye, a phrase so ordinary it barely registers. But Parker meant it exactly, literally, geologically. He was saying that something blinked, that something, for the first time, opened and used an eye, and that in the geological equivalent of the instant before and the instant after that blink, the world changed completely. The core of the hypothesis is almost elegant in its logic once you hear it stated plainly. Before image-forming eyes existed, before any animal anywhere had a structure capable of resolving a spatial image, of seeing not just light or dark, but direction, shape, the outline of a body moving through water. Sunlight fell on the ocean and accomplished very little for the animals living in it. Light existed. It had always existed, filtering down through the water column above those soft Ediacaran fronds and discs, reaching the sea floor, carrying enormous amounts of information about where everything was. But no animal had the equipment to read it. The light arrived, and it was wasted. Then Parker's hypothesis says something evolved the first true image-forming eye. And in that moment, sunlight became information. Specifically, it became lethal information. Because the first animal that could form an image, that could look across a stretch of water and perceive the shape and movement of another animal at a distance before that other animal arrived, the first animal that could do that was not simply better at surviving. It was transformed into something that had never existed before. A visual predator. A creature that could use light to predict, to locate, to strike before its prey had any indication it was being seen. Parker's argument is that this one change, the arrival of the first image-forming eye, was not merely an addition to the existing world, it was a trigger, a switch being thrown, because once one animal in the ocean could see, every other animal in that ocean was suddenly radically, catastrophically vulnerable in a way it had never been before. Every soft, slow, unarmored body in the sea had spent the previous tens of millions of years in a world where the main threats were chemical or thermal or osmotic, threats you could not outrun or hide from anyway. So there was no particular advantage to running or hiding. There were no eyes to hide from. There was no gaze to escape. The instant there was a gaze, everything changed. An animal that can be seen needs defenses, and crucially, it needs defenses that are specifically suited to being seen, because the danger is no longer just contact, it is detection at a distance, which means your defenses need to work at a distance too. You need a shell because the predator hits hard and fast. You need spines because being grabbed is now a real possibility. You need speed because you now have a window between being spotted and being caught, and the animal that can close that window fastest wins. You need to burrow, to pull yourself down below the reach of sunlight, below the reach of the gaze. You need eventually your own eyes, because seeing your predator is the only advance warning that makes the difference. This is the arms race that Parker is describing. Not a slow, steady, comfortable escalation over hundreds of millions of years, but a sudden, violent feedback loop, a cascade of pressure that begins the instant the first eye opens and immediately forces every lineage it touches to respond or disappear. The predator gets better eyes, the prey gets thicker shells, the predator gets harder claws, the prey gets faster muscles. Each change creates selection pressure on the other side. The loop accelerates, and the record shows exactly this. Shells, exoskeletons, spines, the first burrows, complex nervous systems, rapidly diversifying body plans, all of it appearing together in the same thin band of rock, at the same narrow window of time. The fossil fingerprint of an arms race, the residue of a war, that is the light switch. That is Parker's idea. Now it is important, and Parker himself has been careful about this, to say what the light switch is and what it is not. It is a hypothesis. A compelling, well-argued, carefully researched hypothesis, built by a scientist who knows more about biological optics than almost anyone else working in this field, and grounded in a real and striking correspondence between the timing of the first eyes and the timing of the explosion. But it is one hypothesis among several, and the question of what triggered the Cambrian explosion is genuinely, honestly, still open. There are other ideas on the table, and they deserve their place. The oxygen argument is the oldest and perhaps the most straightforward. Complex animal life needs oxygen in quantities the early Earth could not provide. For most of the planet's history, atmospheric and oceanic oxygen levels were far too low to sustain the metabolic demands of active, predatory, hard-bodied animals. The evidence suggests that oxygen levels rose significantly in the late Ediacaran and into the Cambrian, and it is reasonable to argue that the explosion could not have happened without that rise. That the animals were simply waiting, metabolically, for the air and water to be breathable enough. Oxygen as permission, as prerequisite, as the unlocking of a door that had been sealed for billions of years. Then there is ocean chemistry, and specifically the calcium question. Hard shells and exoskeletons are made of minerals. They require calcium carbonate or calcium phosphate in quantities that have to be dissolved in the seawater an animal lives in. The geochemical record suggests that calcium availability in the Cambrian oceans was rising during exactly this period, which would mean that biomineralization, the biological trick of depositing hard mineral structures, became not just evolutionarily useful but chemically feasible in a way it had not quite been before. The ocean was, in a sense, loading the materials into the biological machinery that was about to use them. And then there is the genetic argument, which goes deepest of all. Animals are built by genes, and the instructions for building complex bilateral bodies with a front and back, a head and tail, symmetrical pairs of limbs, those instructions are encoded in a family of regulatory genes called Hox genes. The Hox genes are the master architects of the animal body plan. They tell an embryo which end is which, where to build the nervous system, where to grow limbs and eyes and organs. And it appears that by the beginning of the Cambrian, the genetic toolkit for building complex animals had been quietly assembled over the preceding hundreds of millions of years, reaching a kind of developmental richness and flexibility that suddenly made an enormous variety of body plans possible to explore. The explosion, on this account, is partly a genetic event. The moment when the instructions set for building animals reached a threshold of complexity that could generate, in rapid evolutionary experimentation, most of the basic body plan templates that have existed ever since. All of these are real, serious, evidence-based ideas. Any honest account of the Cambrian explosion has to hold them together and acknowledge that the trigger was probably not one thing, but several, a convergence, a coincidence of conditions, each of which was necessary, but none of which alone was sufficient. The oxygen had to be there, the chemistry had to cooperate, the genetic toolkit had to be ready. And then, Parker would argue, the first eye had to open, because Parker is not claiming that eyes alone caused the explosion without the oxygen, without the chemistry, without the genes. He is claiming something more specific. He is claiming that among all the changes that were accumulating in the late Ediacaran and early Cambrian, the one that converted the accumulation into an avalanche, the one that turned a gradual background rate of evolutionary change into a sudden, catastrophic, cascading transformation, was the one that put useful, actionable information into the world for the first time. Sunlight had always been present. The photons had always been falling. The chemistry and the oxygen had been building, but none of it became a pressure until something could see it, until a predator could read the light and use what it read to hunt. This is the switch, not the invention of light, but the invention of vision, not a new source of energy, but a new kind of information. It is worth sitting with that distinction for a moment because it is the hinge of the whole idea. Before image-forming eyes, the ocean was full of information. chemical gradients, pressure waves, electrical fields, shadows, and animals had been using various versions of these for a very long time. Simple photoreceptors, patches of cells that could detect the difference between light and dark, register the passage of a shadow, sense whether you were facing toward the sun or away from it. These had existed for a long time before the Cambrian. The capacity to detect light is ancient. Even single-celled organisms respond to light in basic ways. Light sensitivity alone did not change the world. What changed the world was spatial resolution, the ability to form an image, to not just detect that there is light, but to perceive the structure of the light field, to distinguish that over there is a shadow in the shape of something large and moving, and it is approaching from the left, and it is moving at this speed. An eye that forms an image is not merely better at detecting light, it is doing something categorically different from a simple photoreceptor. It is constructing a model of the space around the animal. It is turning photons into a picture. And that picture is prediction. Think of it this way. A temperature sensor tells you it is cold. An image-forming eye tells you that a large thing with grasping appendages is moving toward you from across the water at a speed that will bring it into contact with you in approximately 3 seconds. The difference between those two pieces of information is the difference between discomfort and death. One of them gives you time to act. One of them, crucially, gives you information about something that has not yet touched you, that is still over there, still at a distance, still in the future of its trajectory toward you. An eye is a device for knowing what is about to happen before it happens. It converts the present arrangement of light into a prediction about the near future. It is, at its core, a machine for buying time. And that purchase of time is what makes vision so different from every other sense in the arms race calculation. Chemical senses tell you something is nearby, but by the time the chemical reaches you, the thing producing it may already be very close, already past the horizon where flight could save you. Pressure senses, the lateral lines that fish use, can detect movement in the water, but they are close-range senses, useful when the predator is already nearly upon you. Vision works at distance. It gives warning across meters of open water, across a field of view, across time. It is the only sense that routinely delivers information about threats that are still far enough away that escape is possible. This is why, once it appeared, it changed everything so fast. But here is a question that is worth asking and that the light switch hypothesis has to answer. If image-forming vision is this powerful, this advantageous, why did it not happen sooner? Why did the first eye wait until approximately 521 million years ago? Life had been in the oceans for more than 3 billion years before this. Photons had been falling on the sea for all of that time. Simple light sensing had existed for hundreds of millions of years before the Cambrian. Why did it take so long for something to build the first true eye? The answer is not simple, and it probably involves several things converging at once. Part of the answer is genetic. An eye is not just a lens. An eye is a lens, yes, but it is also a retina, a set of photoreceptor cells arranged in a spatial array and wired to a nervous system that can interpret their signals as a spatially organized image. Building an eye from scratch requires not just the structural proteins that make a transparent lens, but the light-sensitive proteins, the opsins, that the retinal cells use to convert photons into electrical signals, and the neural wiring that takes those signals and constructs from them a coherent representation of the space in front of the animal. That is an enormously complex system involving many different genes working in precise coordination. It did not appear overnight. The components assembled over hundreds of millions of years. The opsins diversifying slowly, the gene regulatory networks gradually acquiring the capacity to build a spatially organized array of receptors, the nervous system's gradually developing the processing capacity to do something useful with the image once they had it. And at the center of all of this, there is one gene, one master regulatory gene that sits at the top of the eye-building hierarchy, and when it is switched on in a developing embryo, instructs the tissue beneath it to build an eye. That gene is called PAX6. PAX6 is extraordinary. It is the same gene in a human embryo, and in a fruit fly embryo, and in a mouse embryo, and in a squid embryo. The same gene, or very nearly the same, building eyes of radically different designs in animals that last shared a common ancestor more than 500 million years ago. A camera eye in a vertebrate, a compound eye in an insect, a pinhole eye in a nautilus, all of them built under the instruction of this one ancient master switch. You can take the mouse version of PAX6 and introduce it into a fruit fly embryo, and the fly will grow eyes, not mouse eyes, but fly eyes. The PAX6 gene activates the local eye-building machinery wherever it is expressed, and that machinery in the fly builds fly eyes. The gene is not a blueprint for a specific eye design. It is a command: build an eye here. Whatever kind of eye you know how to build it here. Now, this deep conservation of PAX6 across almost all animals with eyes tells us something remarkable. It tells us that the genetic program for eye construction has a single ancient origin, predating the Cambrian, predating the divergence of the major animal lineages from one another. The gene was there before the eyes diversified. The instruction was in the genome before the structures it instructs appeared in their full, elaborated form in the fossil record. In some sense, animals were genetically ready to build eyes before they built them, waiting for the ecological and environmental conditions that would make building them worthwhile. And this brings in the second part of the answer, which is ecological. Vision only pays in the presence of light. An eye is metabolically expensive. The neural tissue needed to process visual information is among the most energetically costly tissue in the body. You do not evolve and maintain an expensive structure unless it gives you a benefit large enough to justify the cost. And in the deep ocean, where no sunlight penetrates, an eye is useless. In a world where predators were rare or absent, an eye to detect them offers little advantage. The investment in an eye, in the neural wiring to process its signals, in the behavioral flexibility to act on what it shows you, all of that investment only begins to pay off when there is enough light to see by and enough predation pressure to make seeing worth the cost. This is the photic zone argument. Sunlight penetrates clear seawater, but only to a certain depth. Below roughly 200 meters in clear open ocean, light fades toward nothing, and below that, the sea is dark. The zone of light, the photic zone, the sunlit upper layer where photosynthesis happens and where vision is physically possible. That zone has been where the greatest density of marine life has always concentrated, because that is where the energy from sunlight enters the food chain. And the Cambrian arms race, the evidence suggests, was concentrated there. It was a war fought in the light, in the shallow, sunlit coastal seas and continental shelves where the Cambrian animals lived most densely, where the energy was richest, and where the light was bright enough to make image-forming eyes worth building and maintaining. Before the explosion in the Ediacaran garden, the ecological density may simply not have been high enough, the predation pressure not intense enough, the prey not plentiful enough to make the arms race pay off clear. PAX6 was waiting in the genome. The opsins were there. The basic photoreceptor cells existed, but the ecological incentive to fully elaborate the machinery, to invest in the processing power to turn a spatial light field into a coherent image, may not have been sufficient. The conditions were not yet right. And then they became right. The oxygen was there. The calcium was there. The genetic toolkit was rich enough. The ecological density in the shallow, sunlit seas was reaching a threshold. And somewhere in that convergence, in some lineage we may never be able to identify with certainty, some soft-bodied ancestor of what would become the arthropods, or something close to them. The image-forming eye appeared, and the light switch was thrown. It is worth pausing here, in the dark of wherever you are lying, and trying to feel what that moment would have been like. Not from the predator's point of view, but from the prey's. For tens of millions of years, the most you had to fear in the Ediacaran Sea was chemical change, a shifting in the composition of the water around you, or a slow pressure, something touching you. Threats arrived by contact. There was no gaze in the world. Nothing could see you from across the water. Nothing knew you were there until it was close enough to feel you, and by that point the interaction was already happening, and your options were already almost gone. You were invisible at any distance. Every other animal in the sea was as blind as you were. And then, in geological terms, almost instantaneously, something could see, could look across the water and perceive your outline, your movement, your precise location from a distance, could form a picture of you before you had any idea you were being watched, could launch an attack with the full advantage of surprise and information on its side while you were still operating on the old set of rules, the Ediacaran rules, where threats arrived by touch and there was nothing to run from before it touched you. The pressure that created must have been immense and immediate, because the animals that did not respond to it, that did not by some genetic accident produce a shell, a spine, a burrowing behavior, a faster escape reflex, an eye of their own, those animals left the shallows or they disappeared. The ones that remained in the record are the ones that found an answer, and their answers are what we see in the rock. The shells and exoskeletons and spines and burrows and compound eyes and nervous systems, all of them appearing in that one thin, bright seam, all of them responses to the same pressure, the same sudden fact about the world that had not been true before, the fact that something can see you. Parker wrote in the years after the book that he thought of sunlight as having been switched on for the first time as biologically useful information at this moment. Not that the sun had not been shining before, but that before image-forming eyes, sunlight carried no information that any animal was equipped to read at a distance. It fell on the sea and was absorbed or reflected and did nothing that mattered to a predator-prey interaction. And then, with the first true eye, it began to carry everything. The position and movement of every illuminated body in the water column, the full spatial layout of the sunlit sea, updated in real time, available to any animal equipped to read it. That is a profound change in what the world is, not a change in the world's physics, and the light had always been there, but a change in what the world means to the animals inside it, a change in the information content of the environment as experienced by living things. Before the eye, sunlight was scenery. After the eye, sunlight was intelligence. And here, resting in the dark, you can feel the faint echo of this in yourself. You are lying with your eyes closed, and the darkness is comfortable. And part of why it is comfortable is that it is your darkness. Chosen, contained, safe. But notice that the darkness outside your window, the darkness you cannot control, the darkness in which something might be moving that you cannot see, that darkness does not feel quite the same. There is an old unease in the dark, an unease that is not rational, that does not correspond to any real threat in your bedroom or wherever you are, but that sits below the level of reason, a very faint, very ancient discomfort with the condition of not being able to see what might be seeing you. That unease is very old. It is the echo of the prey in the Ediacaran Sea, the soft animal suddenly in a world where something could look at it from across the water. The era of being watched, of being findable by light, had begun. And the deepest layers of animal nervous systems, the layers that were written into the biological program before language, before memory, Before thought in any form you would recognize those layers, remember that the dark was the one place a visual predator could not reach, and that stepping out of it into the light was the moment you became visible. You are right now doing what your ancestors learned to do in the Cambrian, resting in the dark, out of the photic zone, out of the gaze, and something in you, something layered deep below the rational mind, knows that this is where it is safe. But we are getting ahead of ourselves, because before we can understand the arms race that followed the light switch, we need to understand the eyes themselves, what they actually were, what material they were made of, how they worked, and what kind of sight they gave to the animals that had them. We need to understand what it actually meant, in physical, optical, biological terms, to be among the first seeing things in the history of animal life. And to do that, we need to look at the eyes that left a record we can actually examine. Not the soft tissue eyes that dissolved without a trace, but the eyes that did something no other eyes in the entire subsequent history of animal vision have ever done. The eyes that were made of stone. Because there is an animal in the Cambrian record, an animal that appeared very early, that spread to nearly every marine environment on the planet, that would diversify into thousands of species and persist for more than 270 million years. And this animal had eyes unlike anything that has ever existed before or since. Not compound eyes made of chitin and protein like the eyes of a modern insect. Not camera eyes made of water and protein like yours. Eyes made of a mineral. Eyes grown from crystals of calcium carbonate, clear as glass, hard as rock, durable enough to survive in the fossil record not as impressions or traces, but as the original optical material itself, still transparent, still structured, still, astonishingly, in some cases, still capable of transmitting light. This animal is the Trilobite, and the story of its eyes is the story of how evolution solved 500 million years ago an optics problem so subtle that human mathematicians did not formally describe it until the 17th century. The Trilobite first appears in the fossil record approximately 521 million years ago, and it appears not as a transitional, half-formed sketch of an animal, but as something already complete, already sophisticated, already wearing in its head a pair of eyes that would take the best human optical theorists another 500 million years to fully understand. They were arthropods distantly related to the crabs and insects and spiders of today, though the lineage they belong to is now entirely extinct. They crawled across the seafloor and swam through the water column and burrowed into the sediment, and they did all of these things in enormous variety. There were trilobites with eyes perched on long stalks, trilobites with eyes pointing downward to watch the sea floor, trilobites that had apparently lost their eyes altogether in the darkness of the deep, and trilobites with eyes so large relative to their bodies that they seem almost cartoonish, animals built almost entirely around the project of seeing. More than 20,000 described species, spread across more than 270 million years of geological time, making trilobites one of the most successful groups of complex animals that has ever lived. And threaded through nearly all of that diversity in nearly all of that time were those eyes, those extraordinary, improbable, geologically impossible eyes. Impossible because a lens, in any modern optical system you can name, is made of something transparent but soft. Glass, plastic, protein suspended in fluid. Something that can be shaped, curved, polished, molded into precisely the geometry that the physics of light demands. The cornea of your eye is protein. The lens behind it is protein. The compound eyes of an insect are covered by a transparent cuticle made of chitin, organic, flexible in its construction, even if hard in its final form. Every eye that currently exists on this planet is built from organic material, because organic material can be sculpted into the subtle curved surfaces that bending light requires. Trilobite eyes were not. Trilobite lenses were made of calcite, calcium carbonate, the same mineral that forms limestone, that forms chalk, that forms the shells of oysters and the skeletons of coral. A crystal, rigid, non-negotiable in its structure, grown atom by atom according to the inflexible rules of crystalline geometry. And here is the first astonishment. Calcite is, under certain conditions, transparent, not opaque like most rock. Transparent in the way that a window is transparent, in the way that a glass marble is transparent, clear enough that light passes through it, clear enough that an eye built from it could, in principle, see. And so the trilobite grew lenses the way a shell grows, not sculpted by some biological process of careful protein folding, but accreted, mineral by mineral, into a form that the laws of crystallography and the laws of optics somehow, between them, accommodated. You can hold a trilobite fossil and look at the eye, and what you are looking at is not an impression, not a ghost, not a mineral replacement of the original tissue. What you are looking at, in many exceptionally preserved specimens, is the original lens material. 500 million years old and still there. Still clear. Still, in principle, capable of bending light. There is almost nothing else like this in the history of fossilized biology. Soft eyes, the protein eyes of shrimps, of worms, of fish, dissolve. They leave no record of themselves. Even the hard eyes of insects made of tough chitin rarely survive in any optically meaningful form, but calcite does not dissolve. Calcite persists. And so the trilobite eye, alone among all the eyes that have ever lived, gives us the actual optics, the real geometry, the genuine instrument of ancient sight handed across 500 million years of time in a form we can still measure. Riccardo Levi-Setti, a physicist at the University of Chicago, spent years in the latter half of the 20th century studying trilobite eyes with the precision his discipline demanded, applying the mathematics of optics to structures that had been grown before the first human being existed, and what he found was extraordinary. The lenses were not simply globs of calcite pressed into roughly spherical shapes. They were precisely formed. They were optically engineered, not by an engineer, of course, not by any conscious intention, but by the ruthless logic of natural selection, acting over millions of years on the inherited variation in how calcite crystals assembled themselves within the growing trilobite. The result was a lens geometry that, when Levi-Setti ran the numbers, matched solutions that the human mathematicians René Descartes and Christian Huygens had independently arrived at in the 17th century. Let that settle for a moment, because it is not a small thing. Descartes and Huygens were working on a fundamental problem in optics. How do you design a lens that brings all incoming parallel rays of light to a single point of focus, rather than allowing the edges of the lens to focus slightly differently from the center? This problem has a name. It is called spherical aberration, and it is one of the central challenges in the design of any precision optical instrument. A simple spherical lens, the kind you might intuitively imagine carving, a smooth dome of glass, does not solve it. Light hitting the outer edges of a spherical lens bends at a slightly different angle than light hitting the center, and the result is a slightly blurry image with different focal points fighting one another. To correct for spherical aberration, you need a lens with a more complex, mathematically specific curved surface, a surface whose exact shape can be derived from the equations governing the refraction of light. Descartes derived the shape. Huygens derived it. Human mathematicians working with pen and paper and the accumulated framework of 17th century mathematics solved this particular optical problem and arrived at a specific lens geometry. Trilobites had solved it 500 million years earlier. Their lenses, particularly in the species belonging to the group called the schizochrole trilobites, were not simple single-element calcite domes. They were doublet lenses, two elements, two subtly different curved surfaces stacked together. And the geometry of those surfaces, when measured and calculated, corresponds to the corrective optical design that removes spherical aberration. The trilobite eye was not approximating good optics, it was achieving something close to optimal optics for its material and its physical constraints, using a solution that human intelligence took until the 1600s to derive, and that evolution had apparently converged upon through the blind pressure of predator and prey, light and shadow, seeing and being seen. Phacops is perhaps the most studied of the schizochrole trilobites. It is a genus whose fossils are found across a broad span of geological time and across many parts of the world, a comfortable, familiar shape once you have seen it. That domed, segmented body, those large, distinctly faceted eyes looking out from either side of the head. Each eye of Phacops contained relatively few individual lenses compared to some trilobite eyes, dozens rather than hundreds or thousands. But each of those lenses was large, separated from its neighbors, and constructed as a doublet with that correcting internal surface built in. The schizochrole eye appears to have been optimized less for wide-angle coverage than for the quality of the image each individual lens produced. Fewer, better lenses. Resolution over coverage. The alternative design, the holochrole eye found in many other trilobite groups, packed far more lenses together, covering a much wider visual field, the lenses touching their neighbors, the whole surface of the eye, a continuous array of tiny optical elements, more like what you might imagine when you picture a modern insect's compound eye, though the material was still calcite, still mineral, still rock, grown into transparency. Depending on the trilobite species, the number of lenses in a holochrole eye could range from a handful to several hundred, and the visual experience, if we can even try to imagine it, would have been something like a mosaic, a pixelated but wide-angle picture of the Cambrian Sea, a grid of slightly overlapping views stitched into a single field of perception. Neither design is primitive, neither design is the rough first sketch of a system that would later be improved. Both designs were, for their constraints and their purposes, working solutions. And the reason we know this, the reason we can say it with confidence rather than just inferring it hopefully, is that we have the lenses, the actual material, the original calcite. We can measure the geometry. We can calculate the optics. The evidence is not inferential, it is physical, 500 million years old and still largely intact. But calcite presents a problem that the trilobite needed to solve, and the solution to that problem is itself another layer of the marvel. Calcite, unlike glass, unlike the proteins that build your own lens, is birefringent. This is a property of the crystalline structure, an inevitable consequence of the way calcite atoms pack themselves together. And what it means in practical terms is this. A single ray of light entering a calcite crystal does not remain a single ray. It splits. Calcite separates light into two components traveling at slightly different speeds through the crystal, following slightly different paths, arriving at slightly different places on the other side. If you place a piece of calcite over text on a page, you see the text doubled. Two slightly offset images, both equally real, both equally visible, because the crystal has divided the light that carries the image into two distinct beams. An eye made of birefringent calcite, if the crystal were oriented carelessly, would not produce a single image. It would produce two. A doubled, ghostly, blurred world, which is to say, it would produce almost no useful visual information at all. An eye that sees everything twice is arguably worse than no eye because it generates confusion rather than clarity. The trilobites solved this. And the solution is elegant in the way that all the best evolutionary solutions are elegant, not clever in any designed sense, but inevitable in retrospect. A solution hidden inside the constraints of the problem itself. Calcite's birefringence depends on crystal orientation. Rotate the crystal to a specific angle relative to the direction of incoming light. Orient the lens along what crystallographers call the optical C-axis of the calcite, and the birefringence essentially disappears. Light traveling along the C-axis does not split. It passes through as a single beam, clean and focused, and the eye that grows its lenses aligned along this axis sees a single, clear image. Trilobite lenses were oriented along the C-axis. Each lens, grown atom by atom in the developing trilobite, assembled itself into the orientation that cancelled the doubling effect inherent in its own material. Whether this happened through direct genetic control of the crystal growth or through some biomechanical process we have not fully traced, the result was consistent and reliable and reproducible across thousands of species and millions of generations. The trilobite had not circumvented physics, it had read physics. It had found, inside the specific optical properties of the one transparent mineral available to it, the one orientation that permitted clear sight, and it had built its eyes accordingly. You could argue, and it would be difficult to argue against, that this represents one of the finest pieces of optical engineering in the history of life on Earth. Achieved by an animal with no brain, in any sense, we would readily recognize. Achieved before the evolution of vertebrates, before fish, before anything that would eventually lead to mammals, to primates, to the humans, who would, centuries later, sit in laboratories and work out why it worked. And the trilobite was not alone in the Cambrian Sea. There were other eyes, other strategies, other approaches to the project of seeing. The Cambrian was not a world with one seeing animal and all others blind. Once vision had arrived, once the switch, as Andrew Parker argued, had been thrown, it spread, it diversified. It was, in the logic of natural selection, simply too valuable to remain rare. If seeing gave you an advantage, then any inherited variation that improved your sight gave you a greater advantage, and the pressure to see well was applied simultaneously and enormously to every lineage of animal in the sunlit shallows of that ancient sea. Among the beneficiaries of this pressure, or perhaps more accurately, among the architects of the pressure itself, was a creature that has become something of an icon of the Cambrian. An animal so striking in its anatomy and so strange in the history of its scientific interpretation that it occupies a unique place in the story of early life. This is Anomalocaris, and its name means, straightforwardly, abnormal shrimp, a name that came from a mistake, as we will see, and that stuck long after the mistake was corrected. Anomalocaris was large. In a Cambrian world where most animals were measured in millimeters, it could reach half a meter, perhaps more, in exceptional specimens, though the very largest size estimates have been debated and revised over the years as new fossils have emerged. Even at the more conservative end of the range, it was a giant in its context, something that would have been immediately, viscerally visible to any animal capable of seeing it. And Anomalocaris was itself very much capable of seeing. It had eyes, large, prominent, stalked, compound eyes that projected from the sides of its head on short, flexible stalks, giving it a wide, forward-facing visual field, the kind of field that a predator requires to track and intercept moving prey. Between those eyes, at the front of its body, it had two grasping frontal appendages, jointed, flexible, equipped with spines along their inner surfaces, built for reaching out and capturing something. And below those appendages at the front of its body, a circular mouth, ringed with overlapping plates, a structure whose exact function has been debated, whether it was hard enough to crush the shells of armored trilobites, or whether its primary targets were softer, less defended prey? We will come back to that question, but first, the eyes. The eyes of Anomalocaris, or of an animal very closely related to it, have been preserved in extraordinary detail in the Emu Bay Shale of Kangaroo Island, off the southern coast of Australia. The Emu Bay Shale is roughly 513 million years old, which means these eyes are watching us across more than 500 million years, and it belongs to a select group of geological formations that paleontologists call Konservatlagerstätten, a German term for deposits of exceptional preservation, places where the normal processes of decay and burial were interrupted by some chemical or geological condition that allowed soft tissues, and in this case optical structures, to survive. The fossil eyes from the Emu Bay Shale are isolated, detached from the rest of the animal, which is itself not unusual in the violence and tumble of fossil formation. But they are extraordinarily complete. Each eye is a compound eye, built on the same fundamental architectural principle as the eyes of a modern insect or crustacean. Many individual optical units, called ommatidia, packed together into a single domed structure, each unit pointing in a slightly different direction, the whole assembly giving the animal a wide, multi-directional field of view. But the scale is unlike anything in the modern world of insects. Each of these fossil eyes contains more than 3,000 lenses. Some estimates, based on careful examination of the best preserved specimens, go considerably higher, into the range of 16,000 individual optical units in a single eye. Even at the lower estimate of 3,000, you are looking at an eye that, by any reasonable measure, would have produced a clear, detailed, high-resolution image of the Cambrian world. Not the rough sense of light and dark that a simple photoreceptive patch provides, not the blurry directional sense of a simple pit eye, a real image, a picture, objects resolved, distances estimated, movement tracked. This was not primitive vision. This was not the beginning of something that would only much later become sophisticated. This was already, at 513 million years ago, very close to the upper end of what compound vision can achieve. The first image-forming eyes that left us evidence did not arrive as rough drafts. They arrived as something close to a finished design. And consider what that means for the animal that possessed them. Anomalocaris, or whatever apex predator, swam the Emu Bay Sea and lost its eyes to the sediment in that exceptional way, was not groping through the water using chemical gradients and vibration, the way an animal in the pre-vision Ediacaran world might have navigated. It was watching, it was tracking. Light entered those thousands of lenses, was processed by whatever neural machinery lay behind them, and that animal received a picture of its world. It could see the shape of a prey animal moving across the seafloor below. It could see the glint of a trilobite's shell in the shallow, sunlit water. It could calculate, using the slightly different image in each eye, something like depth, something like distance, something like the relative position of a target it intended to close upon. Vision of that quality changes everything about how an animal hunts. It means you can plan, in the simplest sense of the word. You can see where your prey is going and intercept it rather than simply follow it. You can pick the largest, the slowest, the most vulnerable target from a group. You can see the movement of a shell beginning to retract into its armor and time your approach accordingly. You can be, in the most practical and immediate sense, a better predator than anything that has ever existed before you. It was this, the quality and precision of what Anomalocaris apparently saw, combined with the structural weaponry it carried, that made it the dominant predator of the Cambrian, the apex of the food web in the sunlit shallows where the arms race was being fought most intensely. And yet, for most of the history of paleontology, nobody knew that Anomalocaris existed at all. Not because the fossils weren't there, they were there in the rock, waiting to be found, but because nobody understood that the pieces they kept finding were pieces of the same animal. This is one of the stranger, more human stories in the history of paleontology, and it is worth dwelling on for a moment because it tells us something about the difficulty of reconstructing an unfamiliar body plan from fragmentary evidence, and about how long it can take even careful science to see what is in front of it. The appendages of Anomalocaris were the first things found, curved, jointed, spiny structures recovered from Cambrian rock in the 19th century, and they looked to the paleontologists who described them like the bodies of shrimps. Small, segmented, unfamiliar, but recognizably arthropod-like. They named them Anomalocaris, the abnormal shrimp, because that was what the appendage appeared to be. A shrimp, somewhat unusual in form, now found as an isolated fossil with the body seemingly missing. A mystery, certainly, but not an incomprehensible one. Animals are found as isolated pieces all the time. Preservation is selective and incomplete. Separately, in the same Cambrian deposits, paleontologists found something else, a circular structure, flat and ringed, made of overlapping plates with a texture and symmetry that suggested, to the people examining it, a kind of medusoid, a jellyfish. They named it Biota, and it sat in the literature as its own animal, a Cambrian jellyfish of sorts, catalogued and set aside. And separately again a body fossil, it's an oval, flattened shape, the trunk of something, lacking obvious appendages or a head in the portions preserved, which someone identified as a sea cucumber. This one was called Lagania. 3 animals, 3 names, 3 entries in the catalogue of Cambrian life. In the 1980s, a group of paleontologists working primarily out of Cambridge, Harry Whittington and Derek Briggs among them, were engaged in the systematic, painstaking, enormously labor-intensive project of re-examining the fauna of the Burgess Shale and related Cambrian deposits with fresh eyes and new techniques. They were finding things the original describers had missed, seeing structures that preparation and lighting techniques of an earlier era had obscured, and they were increasingly troubled by how often the pieces of the Cambrian fauna seemed to suggest connections that the existing taxonomic categories couldn't accommodate. When they looked carefully at Anomalocaris, the appendage animal, they began to see that the curved, spiny structure was not a shrimp body. It was a frontal appendage, a grasping limb attached to the front of something much larger than anyone had assumed. When they looked at Patia, the jellyfish, they began to see that the circular plated structure was not a medusoid body plan at all. It was a mouth, a circular, toothed, plated mouth designed to close around something. And when they reassembled these pieces, the appendage, the mouth, the body, they found that they fit. Not approximately, not suggestively, but actually and physically fit, as parts of a single, large, bilaterally symmetric, actively swimming predator. Anomalocaris, Paitoia, and Lagania were the same animal. The claws, the mouth, and the body of one creature misidentified as 3 different animals across nearly a century of accumulated scientific literature. The correction when it came was not simply a taxonomic update, it was a reconceptualization of what the Cambrian Sea had actually contained. Because Anomalocaris, reassembled and understood as a coherent animal, was suddenly very large, very capable, very clearly a predator of significant sophistication, and possessed of those remarkable stalked eyes that the fragmentary earlier study had never been able to consider as a whole. It changed the picture of Cambrian ecology in a fundamental way. There was a visual predator at the top of the food chain from very early in the explosion, and everything living in the same waters as Anomalocaris would have been subject to its gaze. Now, about those claws and that mouth. The question of what exactly Anomalocaris ate, and how, has been one of the more productively contentious debates in Cambrian paleontology. The intuitive answer, the one that once seemed obvious from the anatomy, was that Anomalocaris was a trilobite cruncher. It had the right size, it had grasping appendages. It was in the same sea as trilobites, which were present in enormous numbers and would have been a tempting food source. The image that took hold in popular accounts, and in many scientific ones, was of Anomalocaris sweeping through clouds of trilobites, those great spiny appendages closing over armored prey, that circular mouth pressing down onto a shell and crushing through. But the reality, as subsequent work has increasingly suggested, is more complicated. The mouth of Anomalocaris, that ringed petoia structure, may not have been capable of generating enough force to crack mineralized trilobite armor. Biomechanical analyses of the mouth's structure have led some researchers to argue that it would have deformed, buckled, or opened under the compressive stress required to crush a well-armored trilobite, that the mouth was more suited to softer, less defended prey. There are trilobite fossils with bite marks consistent with a circular-mouthed predator, and there are researchers who argue those marks could have been made by Anomalocaris, but there are also researchers who find the mechanical case unconvincing and who suggest the marks may have been made post-mortem or by a different predator. What is less contested is the visual hunting. Whatever Anomalocaris was eating, it found it with those eyes, it tracked it, approached it, assessed it with the image-forming vision that those thousands of fossilized lenses represent. Whether the prey was a soft-bodied worm, a lightly armored arthropod, or an occasional trilobite whose defenses happened to be insufficient against a particular attack, the hunting was visual. The predator saw its prey. That much is written into the fossil record in the form of 16,000 lenses preserved in the rock of Kangaroo Island, staring up at the light of a very different world. And it is worth pausing here, in the middle of this particular piece of the story, to notice something. Because we have been talking about trilobite eyes and the eyes of Anomalocaris as though they are simply interesting anatomical facts, curiosities of ancient biology, things to remark upon and then move past. But the pairing of these two animals, a visual predator of Anomalocaris's capability, and prey animals like the trilobites, whose own elaborate optical engineering suggests they, too, were very much in the business of watching and being watched, is not incidental. It is the arms race itself made concrete. It is Andrew Parker's light switch argument written in stone and calcite and mineral lenses. Anomalocaris sees trilobites develop increasingly sophisticated compound eyes in dozens of different species, in holochrome and schizochrome configurations, with lenses oriented along the optical C-axis to cancel birefringence, with doublet structures that correct for spherical aberration. Because in a sea where something like Anomalocaris is watching, better eyes are not a luxury. Better eyes are survival. The ability to see a shadow moving at the edge of your visual field and to react before it reaches you is the difference between living long enough to reproduce and becoming part of the food chain. Natural selection, in an environment shaped by a visual predator, acts on visual acuity with a force and speed that it cannot achieve in an environment where nothing hunts by sight. And the trilobite, because its eyes were made of calcite, because its lenses survived where every other ancient eye dissolved, hands us the evidence, hands us the actual optics, hands us the geometry of the doublet and the C-axis alignment, and the schizochrome separateness of the lenses in phacops, and lets us look at these things not as approximations or inferences, but as measurements, as calculated solutions to a specific optical problem in a specific physical environment, solutions refined over millions of years of exactly the pressure that Parker's hypothesis describes. The trilobite eye, in this reading, is not just a fascinating fossil. It is a record of the arms race itself, written in the one material durable enough to carry the record forward across 500 million years, And both of these animals, the seeing hunter and the seeing prey, were operating in the same shallow, sunlit stretch of ancient ocean in the photic zone where light penetrated and where vision therefore paid. Where there was enough light to form an image, there was enough light to be seen, and where you could be seen, the pressure to see first and better was relentless. The logic is circular in the way that all arms races are circular. Predator sees better, prey must also see better, or develop other defenses that compensate for the asymmetry of sight. Both paths lead away from the quiet, lightless, imageless prevision world. Both paths lead toward complexity. The trilobites went in both directions simultaneously. Their eyes grew more sophisticated. The doublet lens, the C-axis alignment, the variety of holocrol and schizocrol strategies, and their armor grew too. The shell that covered the trilobite body was, in many species, mineralized, calcified, hardened into something that cost the animal metabolic resources but provided a physical barrier against predation. Not because hardness is inherently valuable, but because in a world with visual predators, hardness is the alternative to speed, and speed is the alternative to eyes, and eyes are the alternative to burrowing, and burrowing is the alternative to armor. And all of these strategies proliferate simultaneously because the pressure that generates them applies to every animal that can be seen. This is the cascade. This is what the light switch argument is actually describing. Not just the evolution of eyes, but the evolution of everything that eyes made necessary. And so we arrive at the fingerprint, the record left in the rock of what happened when seeing became possible, when the arms race was no longer theoretical, but written into bone and shell and the compressed layers of ancient seafloor. What we find when we look closely at the Cambrian strata is not a single adaptation, but a convergence, a clustering of innovations that appear together in the geological column, arriving within the same compressed window of time, as if summoned by a single pressure. Shells, exoskeletons, spines, burrows, the whole vocabulary of defense appearing at once from lineages that had no shared ancestor, as though the same message had been broadcast to every animal in the sea and each had translated it differently but urgently. This clustering is the fingerprint. It is what makes the arms race interpretation compelling, because if hard parts had evolved for some other reason, if shells were simply useful in some abstract metabolic sense, or if burrowing was driven purely by changes in sediment chemistry, you would not expect them to appear simultaneously across unrelated lineages in the same geological moment. You would expect them to appear piecemeal, in different places at different times with different triggers. Instead, what the rock shows is a coordinated response, as though the ocean had asked a single new question and every living thing had been forced to answer it at once. The question, of course, was whether you could be seen. Biomineralization, the biological process of building hard structures from dissolved minerals, had existed in rudimentary forms before the Cambrian, but the Cambrian saw its sudden, widespread adoption as a body strategy. Calcium carbonate, calcium phosphate, silica. These minerals were already dissolved in the ancient ocean, waiting. Animals began pulling them from the water and incorporating them into shells, plates, tubes and spines with a speed that, in geological terms, is extraordinary. Not over hundreds of millions of years, but within a geological eye blink, the soft-bodied ocean began to grow armor. The Ediacaran seas had been, with rare exceptions, a world of bodies that left no hard impression. The earliest Cambrian strata are suddenly dense with mineralized remains. The small, shelly fossils, as they are called, a scattering of tubes and plates and shells whose owners we sometimes still struggle to identify, but whose existence is unambiguous. Something changed. Something made hardness worth its metabolic cost. Think for a moment about what building a shell actually requires. It is not free. The calcium has to be pulled from the surrounding water, transported inside the body, deposited in precisely controlled layers. The animal that builds a shell is spending energy that might otherwise go toward reproduction or growth or movement. A shell is a capital investment, and like all capital investments, it only makes sense if there is a threat to insure against. In a calm, imageless sea, a shell is expensive and unnecessary. In a sea with seeing predators, a shell is survival. The sudden proliferation of hard parts is, in this reading, a ledger entry. Here is what the ocean calculated it was worth spending to stay alive once something was looking. The spines are perhaps even more telling. A spine is not just passive armor. A spine is a message. It says, even if you can reach me, the cost of taking me will be high. Spines evolved independently in multiple lineages within this same compressed window. They are not a shared inheritance, but a shared solution, arrived at separately by bodies that faced the same new problem. A predator that could see well enough to select targets based on their appearance, their movement, their apparent vulnerability. A spine makes you look less worth the effort. It is the first recorded instance of animal advertising, of bodies broadcasting information about their own defensive capabilities to an observer. And an observer is, specifically, what the new predator had become. Burrowing tells a different story, but one with the same logic underneath. The agronomic revolution, as paleontologists sometimes call it, or the substrate revolution, refers to the dramatic shift in how animals interacted with the seafloor that occurs right at the Ediacaran-Cambrian transition. The Ediacaran seafloor had been, for the most part, a mat world. Thick microbial mats covered the sediment, and most animal life lived on top of them or just at the surface. The earliest Cambrian trace fossils, the marks and tunnels left in sediment by moving bodies which preserve even when the bodies themselves do not, show animals beginning to move into the sediment, to burrow downward, to leave the surface and hide. This is not a response to some abstract environmental change. It is escape. The surface had become dangerous. Something on the surface could now find you by sight, and the only defense available to a slow-moving, soft-bodied animal was to go somewhere the light did not reach, somewhere a visual predator could not easily follow. The burrows are holes in the rock that say, "I was afraid." And they appear precisely when the eyes appear, not before. This co-occurrence, eyes and armor and spines and burrows all arriving together in the same geological moment, is the Red Queen playing her first hand. The Red Queen hypothesis, named after the character in Lewis Carroll who must run as fast as she can just to stay in the same place, describes the evolutionary dynamic in which predator and prey are locked in a perpetual escalation, each improvement in one driving an improvement in the other, so that the total amount of relative danger in the system stays roughly constant, even as absolute capabilities increase on both sides. Both are always running, neither gets ahead permanently. The Cambrian was the Red Queen's opening move. Before Vision, the game was barely being played. Ediacaran life had predators in some sense. There are traces of grazing and possible predation even in the older record, but nothing like the accelerating, feedback-driven escalation that the arms race model describes. Vision created the condition for a true Red Queen dynamic because it made predation a function of information. Once a predator could form an image, every visible feature of its prey became a potential selection target. Color, shape, movement, size, the presence or absence of protective structures. The prey that happened to be slightly harder, slightly spiner, slightly faster, slightly more camouflaged than its neighbors, was more likely to survive long enough to reproduce, and the offspring that inherited those features would themselves be under the same pressure to be just a little harder, a little faster, a little better hidden. The predator, meanwhile, was being selected for eyes that could resolve finer detail, appendages that could penetrate better armor, bodies that could move faster in pursuit. Both sides were being sculpted simultaneously by the fact of being seen. And this is where the arms race becomes something larger than a story about individual animals, because the consequence of escalating arms races is not just that individual predators and individual prey get better at their respective jobs. The consequence is that the entire ecological structure of the ocean is reorganized. Animals that had previously needed to do very little, to absorb nutrients from the water, to drift in slow currents, to rest on the sea floor without hiding, were suddenly required to have opinions about their environment, to respond to threats at speed, to move, to choose. Behavior became, for the first time, a matter of survival in a way it had not been before. And behavior requires a nervous system sophisticated enough to drive it. This is where vision begins to rewire the animal from the inside. An eye is not a self-contained instrument. It is the front end of a processing chain, and the processing chain is the brain. A simple, light-sensitive patch, a photoreceptor, with no spatial resolution, can tell an animal whether it is light or dark, and this information is cheap to process. But an image-forming eye, an eye with hundreds or thousands of lenses, each pointing in a slightly different direction, each feeding information about a different piece of the visual field, produces a flood of spatial data that has to be integrated, compared, and acted upon in something close to real time. If a predator is swimming toward you from the left, you need to know not just that something is happening, but where it is, how fast it is moving, which direction you should flee. That kind of computation requires neural architecture that is qualitatively more complex than anything needed for simple photosensation. The Cambrian fossil record, in its most exceptional preservation windows, lets us see this neural complexity beginning to appear. The Chengjiang Biota of Yunnan province in southern China, dating to approximately 518 million years ago, is one of those extraordinary preservation windows where soft tissue survives. Not just shells and exoskeletons, not just the hard parts that typically make it into the rock, but eyes and guts, and, in some remarkable specimens, something resembling brain tissue. The Chengjiang animals include early arthropods whose fossilized remains preserve neural lobes, optic stalks, the basic architecture of what would become the arthropod brain. These are not large or elaborate brains by any modern standard, but they are more complex than anything that needs to exist in a world without vision, and they are there already in animals that lived just 20 million years or so after the Cambrian's opening boundary. 20 million years sounds like a long time. It is not in evolutionary terms. Set against the 2 billion years of microbial life that preceded complex animals, 20 million years is a sprint. And in that sprint, from the first image-forming eyes to the preserved neural architecture of Chengjiang, the animal brain had already made the fundamental transition from a simple relay of sensory signals to something that could process a visual scene. Consider what that means in practical terms. An animal in the Chengjiang Sea, looking out through its compound eye at a field of perhaps 3,000 separate lenses, was receiving 3,000 simultaneous signals from 3,000 slightly different directions, all arriving at the same moment and all requiring integration. The brain that handled this had to be organized in layers: input, processing, output. And it had to be fast, because the world that vision reveals moves in real time, and the responses it demands must match that speed. The neural investment was enormous relative to what had come before. And because neural tissue is metabolically expensive, because brains are among the most energetically costly organs an animal can build, the only justification for making that investment is that the information the brain processes is worth more than its cost. Vision made it worth the cost. Vision made a large brain an asset rather than a liability, because vision gave the brain something to do that was worth doing. Before image-forming eyes, a more complex nervous system offered diminishing returns. There was only so much information coming in from the environment and only so much behavior that complexity could usefully generate. After image-forming eyes, a more complex nervous system was the difference between eating and being eaten. The two things drove each other. Better eyes demanded better brains to process what they saw, and better brains made better eyes more useful because a sophisticated visual processor could extract more prediction from the same stream of photons. Alongside the structural evolution of eyes and brains, something was happening at the molecular level that would prove to be among the deepest legacies of this moment. The opsins, the light-sensitive proteins that sit within photoreceptor cells and convert incoming photons into electrical signals, were diversifying. Opsin genes are ancient. Some form of opsin-based photosensitivity predates the Cambrian by a long margin, but the Cambrian saw an expansion and diversification of opsin gene families that corresponds to the expansion of image-forming vision and the new demands of visual ecology. Different opsins are sensitive to different wavelengths of light, and an animal with multiple opsin types can discriminate between colors rather than simply between light and dark. Color vision is, in the context of the arms race, an enormous advantage. A predator that can distinguish the cryptic coloration of its prey, that can see through camouflage by detecting wavelength differences a simpler eye would miss, is operating at a higher level of visual resolution than one that sees only in grayscale. The diversification of opsins in the Cambrian was the molecular substrate of color vision beginning to appear in the animal world, and with color vision came the next layer of the arms race, camouflage. If predators could see color, then prey that could match the color of their background were less likely to be detected. If prey could be camouflaged, predators needed even better color discrimination to find them. The Red Queen extended her domain into the spectrum of light, and the ocean began producing animals whose surfaces were shaped not just by their own structural needs, but by the visual system of the animal looking at them. The Burgess Shale of British Columbia, Canada, dating to approximately 508 million years ago, some 10 million years after Chengjiang, gives us another of these precious windows into the Cambrian Sea, preserved in the fine black shale of what was once an underwater cliff face high in what are now the Canadian Rockies. The Burgess Shale animals are, in many cases, the same kinds of creatures that lived in the Chengjiang Sea a few million years earlier, but their preservation is extraordinary in different ways. The compression of their bodies in the fine-grained sediment captures the outlines of soft tissues, the shapes of eyes, the traces of internal anatomy. Walking through the Burgess Shale fauna is walking through a snapshot of an ocean already deeply transformed by the arms race, an ocean full of animals whose bodies show the signatures of visual predation and the defenses it generated. There are animals with eyes, there are animals with hard, protective coverings. There are animals whose bodies suggest rapid, active movement. There are animals so small and apparently unremarkable that they may have survived by being overlooked, by occupying ecological niches that fell below the threshold of a predator's visual attention. The Burgess Shale is not the beginning of the story. By 508 million years ago, the arms race had been running for perhaps 30 million years, but it is a photograph of the story's early, middle chapters, and what it shows is an ocean organized around the fact of vision in a way that the Ediacaran Sea simply was not. The body plans visible in the Burgess Shale and the Chengjiang Biota, the arthropod plan, the chordate plan, the molluscan plan, the annelid plan, the echinoderm plan, are the body plans that have persisted with modification and elaboration, but without fundamental reinvention for the 500 million years since. This is one of the most remarkable facts in the history of life, and it is easy to say quickly and difficult to fully absorb. The basic architectural templates, the fundamental organizational principles that determine what kinds of bodies are possible, were laid down in a window of perhaps 20 million years during the early Cambrian and have not been superseded since. Every animal alive today, from the nematode in the soil to the blue whale in the Pacific, is an elaboration of a body plan that was already in existence before the Burgess Shale was deposited. This means that the Cambrian was not just an episode of diversification that happened and ended, it was a founding event. The decisions made in that compressed window of biological time, the architectural decisions, the organizational decisions, the sensory decisions, became the boundary conditions within which all subsequent evolution has operated. Eyes did not appear and then become optional. They became, for the vast majority of animal lineages that possess them, so fundamental to how those animals operate that the thought of removing them is almost meaningless. The compound eye of the trilobite, the camera eye that would later develop in the vertebrate line, the extraordinary spatial resolution systems visible in the Emu Bay Shale fossils. These were not experiments that might have been abandoned. They were solutions so effective that they were retained, refined, and elaborated across 500 million years and across every subsequent extinction and recolonization. The arms race that began in the Cambrian never ended. It has simply continued layer upon layer, species upon species, extinction upon extinction, and recovery upon recovery, driven by the same fundamental logic. That vision is prediction, and prediction is survival, and the animal that can predict the world better than its neighbors is more likely to pass its body plan to the next generation. And so we come, finally, to you. You are lying here now in the dark, in a room that your own eyes have already mapped and filed. You closed them not long ago, and in the moment before sleep, your visual system ran a last survey of the familiar space around you. The dim geometry of walls and ceiling, the reassuring stillness of objects that were where they were supposed to be. And then the lights went off, internally, and your brain began its long, nightly project of consolidation and repair. But even in the dark, something in you is still watching. Not with your eyes, which are closed and resting, but with the older, deeper architecture, that vision built over 500 million years of arms race pressure. The gene that built your eyes is called PAX6. It is a master regulatory gene, a switch in genetic terms, that controls the developmental program for eye formation, activating a cascade of downstream genes that together build the eye's structure from a patch of tissue in the embryo. What is remarkable about PAX6 is not just that it builds your eye, or that it built the eyes of every vertebrate whose genome has been examined. What is remarkable is that it also builds the eye of a fly. A fruit fly, Drosophila, with its compound eye of hundreds of facets, is built with the same master switch as the human camera eye, despite the fact that compound eyes and camera eyes are structurally about as different as two eyes can be. The hardware is different, the software is the same. This means that PAX6 is older than the divergence of the vertebrate and arthropod lineages, older than the split between the line that would eventually produce you and the line that would eventually produce a housefly. PAX6 was already in existence, already controlling something before the Cambrian. The eye-building program, in some form, predates the image-forming eyes that the Cambrian produced. What the Cambrian did was take an ancient genetic toolkit, PAX6, and the cascade of genes beneath it, and refine it, under the intense pressure of the arms race, into systems capable of producing the exquisite spatial resolution optics that we see in the Trilobite fossil record, in the Emu Bay Shale eyes, in the preserved optic anatomy of the Chengjiang arthropods. Right now, tonight, in whatever stage of embryonic or childhood or adult life you are, PAX6 is either having already done its work in you or is archived in every cell of your body, a molecular memory of the moment when an ancient genome first learned to build something that could see. The gene that drove the arms race that built the Cambrian Ocean is sitting in your cells, not as a relic, as functional code conserved across more than 500 million years because it is still doing the same job. The opsins in your retina, the proteins that make your photoreceptors sensitive to red light, green light, and blue light, the proteins that allow you to see color and depth and motion, are members of a gene family that was already diversifying in the Cambrian. Your color vision, the ability that lets you distinguish the red of a warning light from the green of a clear sky, traces its molecular lineage back to the opsin diversification that accompanied the first image-forming eyes. The specific opsins are not the same ones a trilobite possessed. 500 million years of evolution has modified and elaborated the protein family enormously. But the family is the same family. The light-sensitive machinery in your eyes was inherited, generation by generation, through an unbroken chain of organisms from the molecular toolkit of the Cambrian arms race. And then there is the behavior. The things you do with your body that you did not choose and cannot fully suppress. The reflexes and instincts that run below the level of deliberate thought. The blink reflex. The involuntary closing of your eyelids when something moves suddenly close to your face. Fires faster than conscious decision. You do not decide to blink at a threat. You blink and only afterwards notice that you blinked. This speed is the point. The blink reflex exists because in a world with visual predators, the fraction of a second between seeing a threat and responding to it is the fraction of a second that determines survival. The reflex runs on the oldest wiring in the nervous system. The pathways that were laid down before conscious deliberation was available as an option. The instinct to freeze when you feel watched. The prickling stillness that comes over a person who senses eyes on the back of their neck, even in a safe room, even when logic says there is nothing to fear, is an echo of the same ancient pressure. Stillness is camouflage in a world where predators hunt by detecting motion. An animal that stopped moving when it sensed the possibility of being seen was more likely to survive than one that kept moving, and that tendency toward stillness under observation was selected for generation after generation until it became so deeply wired that 500 million years of civilization cannot fully override it. You feel watched, you go still, the old machinery runs. The fear of the dark is more complex and perhaps more telling. Darkness means the absence of vision, and the absence of vision in a world organized around visual predation means that the arms race has been switched off in a way that disadvantages you. In the dark, you cannot see a predator coming. In the dark, the information advantage that vision provides is gone, and the ancient neural machinery that evolved to process that information goes, in some sense, anxious. There are no predators in your room. The dark outside your window is the dark of a safe world, or at least a world in which the threats have changed so profoundly that ancient fear of dark machinery is no longer calibrated to them. But the machinery still runs. The mild unease of a truly dark room, the slight elevation of alertness that comes when the last light goes off, the tendency to imagine presences in the shadows. These are the operating system running a program that was written 500 million years ago for an ocean where the darkness at the edge of the photic zone was the boundary between the seen and the unseen, between the predator's world and whatever lay beyond it. You carry all of this, not as metaphor, not as a storyteller's flourish, but as actual inherited structure, genes, proteins, reflexes, neural circuits that was shaped by the event we have been slowly descending into together tonight. The moment when the first image-forming eye opened on the Cambrian seafloor and saw, for the first time, another animal that could now be recognized as prey or predator. The moment when sunlight became information and information became the central pressure of animal life. That moment is still in you. It is in your PAX6 gene. It is in your opsins. It is in the reflex that closes your eye before you finish deciding to close it. It is in the held breath you take when you feel observed. Andrew Parker called his hypothesis the light switch because of the image it conjures, a darkness in which nothing is oriented by vision, and then a switch and light, and suddenly everything in the sea can be located, seen, evaluated by something with eyes. But the switch, once thrown, was never thrown back. The light has been on for 520-odd million years, and all the animal complexity that exists on this planet is, in one way or another, downstream of that first moment of illumination. The shells and the spines and the burrows, the brains and the opsins, the body plans that are still the body plans of every living thing with bilateral symmetry, which is to say, with a left side and a right side, with a front end that leads and a back end that follows, with sensory organs concentrated at the front, where the animal moves first into the world it is trying to predict. Your front end has two eyes in it. The placement was not arbitrary. Eyes at the front, facing forward, provide binocular overlap. The zone where both eyes see the same thing, and the brain can use the small difference between their perspectives to calculate depth, to know how far away something is. Depth perception is what makes it possible to judge distances accurately enough to reach for something, to catch something, to avoid something. The forward-facing arrangement of your eyes is a predator configuration, an inheritance from an ancestral line that hunted by sight and needed to know precisely how far its prey was. You have a predator's eyes. The binocular, depth-resolving, forward-facing visual system you look out through is the system of an animal descended from animals that used vision to locate and reach things. You carry that history in the arrangement of your face, and tonight you have closed those eyes, and the PAX6 gene that built them is quiet, and the opsins in your retina are not receiving any significant photon input, and the neural circuits that process visual information are doing what they do in sleep, consolidating the day's experiences, rehearsing patterns, filing away the images your waking brain collected. The visual cortex does not go dark in sleep. It keeps processing, which is one reason you dream in images, one reason the inner cinema of the sleeping mind is predominantly visual rather than purely abstract. You evolved to be a visual creature in a visual world, and even when the visual world is shut away behind your eyelids, the machinery built for vision keeps running, turning inward. This ocean we have been walking through together tonight, the dark Ediacaran Sea, with its soft fronds drifting in the current, the sudden catastrophic brightness of the Cambrian moment when the first eye opened, the trilobites, with their eyes of transparent stone aligned along the crystal's optical axis to avoid seeing double, the great predator moving through the photic zone with its thousands of lenses reading the shapes of prey against the light, the scramble of armor and spines and burrows, the expanding neural complexity, the proliferating opsins, the diversification of body plans that would never be revised again. All of it happened in a world that is simultaneously impossibly distant and surprisingly close. Close because it is in you. Close because the arms race that began on the Cambrian seafloor is still encoded in the molecules of your retina, in the wiring of your blink reflex, in the mild anxiety of the dark. Close because the gene that built the first image-forming eye is the gene that built yours, and the question it answered, can you see before you are seen, is a question whose answer still shapes the organization of your face and the architecture of your nervous system and the quality of your unease in darkness. The mystery the Cambrian poses is not ultimately a mystery about strange ancient creatures with too many legs or eyes in the wrong places. It is a mystery about causation, about whether one thing, one new capacity, one new form of information available in the world can restructure everything else. Andrew Parker's answer, his light switch hypothesis, is a hypothesis and not a law. The other drivers were real: the oxygen in the atmosphere and the calcium in the ocean, and the expanding genetic toolkit with its master regulatory genes. But the elegance of the light switch image is that it captures something the other explanations do not quite reach, which is the quality of vision as a transformer, as the thing that converts a passive world into an active one, that makes every visible surface into a potential message and every animal into a broadcaster of information it did not choose to send. Before the first eye opened, the Ediacaran Sea was full of life, but it was life that did not need to think about being seen. The soft fronds absorbed the current, the slow disks moved where the chemistry moved them. The ocean was ancient and enormous and utterly indifferent to the problem of being observed. And then something changed in a patch of sea that was shallow enough for sunlight to reach the bottom, in an animal whose genome had, by gradual accumulation, assembled the right combination of photoreceptor proteins and neural processing and optical focusing structures to form, for the first time, a true image of its surroundings, and in that image it saw another animal, and the piece of the Ediacaran was over. Everything that followed, the shells, the spines, the burrows, the brains, the body plans, the 500 million years of escalating complexity, the nervous systems that eventually became complex enough to wonder about their own origins, everything followed from that one switch being thrown. The light came on. The sea learned to see itself. And it has never stopped. The Cambrian seafloor is not somewhere far away in time. It is the foundation of the thing you are lying on, the long chain of bodies and behaviors and genes that connects the first seeing animal to the animal lying here now, in the quiet dark, with its eyes closed and its ancient visual machinery slowly unwinding into sleep. The pressures that built you have been running for 500 million years. Tonight, for a few hours, you can set them down. The opsins are at rest. The PAX6 gene is quiet. The blink reflex will still fire if something moves too close in the dark, but nothing will. The room is still. The shadows are just shadows. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. There are more slow descents like this one here, more old mysteries to sink into whenever you want them. You have done enough for one night. The arms race can wait until morning. The ocean that made you will still be there. The stones that held those ancient eyes will still be there, in the rock, holding their light. Let the deep thoughts settle and let yourself sink with them. Good night. Sleep well.